Now let's talk about some errors that we could potentially make in hypothesis testing. There are some foibles you need to watch out for. Well, first it helps to sort of imagine that there are two potential realities, and we don't know which one of them is true. Not when you do statistics, at least. One is that the null hypothesis really is true. It's actually true. We don't know it yet, but it's really, really true. The other possible reality is that the null hypothesis is false. Your sample didn't come from that population, right? So those are your two possible realities. Only one can be true at any given time. You can't have both the null population being true, the null hypothesis being true, and false at the same time. You got to either have one or the other, right? So these two boxes, right? So this one and this one have to add up to 100%. But these two boxes, this one and this one, have to add up to 1, right? And that's because we have a 100% possibility of this being true and a 100% possibility of this being true. If this is true, this is just not true, right? Okay, so given that this is reality, but we don't know reality, what's the deal? How do we put that together with hypothesis testing? Well, when we do hypothesis testing, we have one of two outcomes. We could either reject the null successfully, that's what we wanted to do, right? We could either reject the null, or we could fail to reject the null. We don't call this accept the alternative, we don't call it accepting the null, sorry. We call it failing to reject, because that's how much we wish we could have rejected the null. We failed to reject the null, okay? Now let's think about these two decisions in conjunction with reality. Here's the thing. When we reject the null hypothesis and say, this sample did not come from this population, if it really didn't come from that population, we would be correct here. This would be a correct decision, right? If this was our decision and this is indeed the world we live in, this is a correct decision, right? If we failed to reject the null, however, we failed, right? We're like, oh, I can't reject the null, right? But the null is actually true. We shouldn't have rejected it. Then this also represents a correct decision. Good job not rejecting the null. The null was right all along, right? So these two are ways that we could be correct. That leaves us two ways that we could be incorrect. So one way is this. We could we could reject the null, successfully reject the null. But the null is actually true. We said, null, you are false. But the null is actually true. This is an incorrect decision, right? And not only that, but we call this a false alarm. Because we were all like, woohoo, we were rejecting that null. Pew, 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 get out of here, right? But false alarm, we shouldn't have actually rejected that null. And this false alarm rate, the probability of that false alarm, is going to be called alpha. It's represented by the term alpha. Now, on the other hand, there is another way, yet another way that we could be wrong. And that way is this. We could fail to reject the null. We could say, I don't know. The null may not be wrong. I don't know, right? We failed to reject it. But the null is wrong. It's false, right? And so this is also an incorrect decision, right? We weren't trigger happy enough, right? This is not called a false alarm. Instead, it's called a miss. Miss, right? And this we're actually going to call the beta rate, right? And so obviously the alpha and the beta have a probability of less than 1 but greater than 0, right? So what we want to do in hypothesis testing is reduce our chance of errors, right? We want to reduce our chance of errors. And we can also figure out what is our probability of getting different kinds of correct decisions. And because we know that this is one version of the world and that should add up to 100%, this probability of failing to reject when we should have, kept the null around, right? This probability is 1 minus alpha. This is sort of what we call, this is sort of just my term, but like a correct failure, right? I mean, it sounds sort of odd, right? But it's like, it's good that you failed, Like, you failed to reject it, and you should have failed to reject it, That's okay. It's like you failed to reject a date, and it's good. That date was really good. He's a good guy, right? Or a good girl. So, you should have failed to reject him. Good, something like that. So correct failure. On the other hand, this is another possible set of what could be right in the world. So this should add up to 100%. So this should be 1 minus beta. That's our rate of correct decision. Where we successfully reject the null, we say, get out of here. And the null is indeed false, right? So in dating, it might be you reject somebody, comes up to you, and good job, you should have rejected them. They're a total loser, right? Okay, so that's what we call a hit. Sort of like in Battleship, you said, pew, right? And you hit it. You hit it on the dot, right? So this is the hit rate. This is the miss rate. This is the false alarm rate. And this is just my word. This is the correct failure rate. All right. So now let's talk about the steps of hypothesis testing. Well, there are going to be 5 steps. And the first step just starts off with setting up your hypothetical population, right? So this is the hypothetical population. And you need to create both a null hypothesis and an alternative hypothesis. Then you want to pick a significance level. So you could think of the word significant as standoutness, right? Like how much it stands out. So how much does it have to stand out? When it stands out a lot, you have a very low false alarm rate, right? So if your X bar is just really out there, right? Then you have a small chance of false alarming. You're saying, this really doesn't look like it belongs in this population because it's so out here. And that's why your false alarm rate is low. You want to set a low one. And if you want to be more conservative, you want to set an even lower false alarm rate. For instance, alpha equals 0.01, right? That would be even lower rate of false alarm. Then you want to set a decision stage. So far we haven't done anything except like setting things up yet. And still we're setting things up. We set up a decision stage. And what you want to do is draw the SDOM, the sampling distribution, right? So remember we have this hypothetical population and we create a sampling distribution so that we could take our sample and compare it to that sampling distribution. So you draw the SDOM and you identify the critical limits. So here's my SDOM. And you want to identify the extreme regions where you say, if your X bar is somewhere out here, right, then you want to reject a null. You reject the null. You want to say it's very, very unlikely to have come from this null population. And then you choose a test statistic because the test statistic will tell you how far out from the mean it is in terms of standard error, right? So how many jumps out you are. And that's and this will be called choose a critical test statistic. So you're saying, what are the boundaries that I'm willing to what are the boundaries, the extreme boundaries, such that if X is outside those boundaries, we reject it. If it's inside those boundaries, we don't reject. And then we use the sample. So this is the first time we're doing anything with the sample. We use the sample and the SDOM, right, from here, to compute the sample's test statistic and p-value. And the p-value is going to tell you, given that x is out here, how much of that curve does it actually cover? What is the probability of false alarming there at that particular value, right? And then you compare the sample to this SDOM population, and you decide reject the null or not. So one word about p-value versus alpha, right? So the p-value is going to be the probability of belonging to the null population, right? Given sample x bar, right? So what is the probability of that this value belongs in here? Alpha is what we call the critical limit. This is what we're able to tolerate. We just said it, right? And alpha is often decided just by the scientific community. In fact, alpha is often set to something like 0.05 or 0.01 because that's commonly accepted in scientific communities. We call that just being by tradition or convention, right? It's not that we figured out the alpha level. On the other hand, we figure out the p-value level given our sample x. And what we want is for the p-value to be lower than the critical limit.